Okay, it's about 8:12 now, so we have to start the class. Okay, Bismillahirrahmanirrahim. Let me go to my slides. Okay. Okay, ji. Bismillahirrahmanirrahim, ji. Welcome to Steel Structures CE 409 in week 5. In this week, we are going to discuss the tension members. Okay, in tension members, what we will discuss in this class will be the failure modes. We will discuss the failure modes in tension members. Then we will discuss the limit states of tension member. Okay, then we will discuss some of the basic concepts like shear lag, block shear failure concepts, and then we see that how we can analyze and design a tension member. And apart from these topics, you also have some solved examples in this lecture. Okay, so when we talk about tension members, so tension members can be found in variety of the structures. Okay, like in truss members you have tension members. In bracing, they can be found in steel structures as bracing members. Similarly, the bracing members in the elevated tanks, for example, if the tank is subjected to a lateral load, okay, so this load is resisted, or this load causes in some of the members tension. Okay, so tension members can be also found in the transmission towers. You can find them as a hanger in buildings. They are also used as hanger in bridges. And for example, for most importantly, in cable stayed bridges, the cables and the hangers we call the suspenders, they are also tension members. Okay, so in short, you can say that any member, okay, any member with the axial force, which is subjected to an axial force like this, is a tension member. Okay, so this is a tension member. Whenever you have an axial force acting through a member, so that is called, we will call it a tension member because it causes tension in the member. Okay, so tension members can be, there are different type of sections which are being used for tension members. Okay, we know that wide flange sections, we know the channels, we know the angles. Okay, and T's, tubes, pipes, rods, cables, plates. So these are the sections which can be used as a tension members. And most importantly, which is the most frequent use cross section for the tension member, is the double angle. Okay, so this double angle is the most frequently used cross section for the tension member. And most importantly, if you see this list, so you might be familiar with these sections. Okay, now this is a double channel. Okay, this is a single channel, this is a one angle, or this is double angle. Okay, apart from these whole hot roll sections, you also have built up sections. So hot roll sections and the built up sections both are used as a tension member. And most importantly, the double angle section is most frequently used cross section as a tension member. Okay, so whenever we talk about tension members, the capacity, or the tensile capacity, you can say that the tensile capacity of tension member is a function of the cross sectional area of the member. Okay, let me write it down: cross sectional area. So this cross-sectional area is very important. You can also say that this cross-sectional area is the only determinant of strength in tension member. Okay, okay, we know that whenever we have a tension member or compression member, so we have to join this member. Okay, for example, you can see in this figure, this is a tension member, this is a bar, or you can assume it as a plate. Okay, so it is subjected to axial force. Okay, so this tension member is connected at supports by some bolts. Okay, And due to the existence or due to the connection or bolted connection, the cross-sectional area in this region is reduced. Okay, so we can term it this cross-sectional area is reduced. Okay, area is reduced due to the presence of holes. So whenever we talk about tension members, there are a different type of areas we will be referring to. So what are those areas? The first area we will use in the analysis or design of tension member, we call it gross area. Okay, gross area means the full cross-sectional area of the member. Okay, the second type of area which we are going to discuss, or which is frequently used or which are being used, is the net area. Okay, and third area, when we have a phenomena called shear lag, so then we will use a different area we call effective area. So up to here, so we have discussed so far that cross-sectional area has influence, a very strong influence. Okay, this is influence on the capacity of tension members. Okay, so what are different type of areas? We have gross area, we have net area, we have effective area. Effective area we use for the scenario when we have a phenomena that occurs in tension member, and you might have seen it on the first slide, the shear lag. Okay, once we have the shear lag phenomena in our tension member, then we are going to use effective area. And where we have to use the net area, you can find it here. When the gross area is subtracted by the whole area, so over here you will use a net area. Okay, this is net area, and this is we have a gross area. Okay, the part of the member in which you don't have any holes, so that over there the cross-sectional area will be the gross area. Okay, so if you look at these sections at this unsupported length of the or unconnected length of the tension member, so you will find a solid section. And when you see this section BB here, in section BB you will have some holes here. Okay, and the holes will be, please remember, the holes diameter, holes dimension, or holes diameter, when we are designing or analyzing a tension member, it should be the diameter of the bolt plus a clearance of 1 by 8 inches. Okay, if you are not given the diameter of the hole and you are only know the diameter of the bolt, so you can calculate the hole diameter by adding a clearance of 1 by 8 inches to the hole diameter. Okay, please remember. Okay, now this is all about the tension members, that different areas which we are going to use in analysis and design of tension area. So there is another statement on this slide that analysis of tension area is a straightforward or simple procedure. Analysis. Okay, analysis of tension member is simple. Design of tension member is iterative. Okay, iterative, and you have to perform or repeat your steps with different assumed values, but it is not very cumbersome, it is very easy. Okay, please remember that what kind of areas we are going to use in the analysis and design of cross-sectional area. So there are that are gross area and net area, effective area. And why we are talking about these areas? Because the cross-sectional area is mainly, or the capacity of tension members mainly depends upon the cross-sectional area. Okay, cross-sectional area. Okay, is that clear to all of you? आप लोगों को समझ आ रही है?
सर ये इफेक्टिव एरिया दोबारा समझाएं।
हाँ, इफेक्टिव एरिया देखें, देर इज अ फिनोमिना कॉल्ड shear lag. Okay, when you have this shear lag phenomena in your member, so then we are going to use a area called effective area. If the grass area is represented by AG, okay, and the net area is EN, and effective area is related to the net area in case of bolted connection by a factor called U. Okay, so this we are going to use effective area in a case when we have a shear lag phenomena. Okay, but if we do not have shear lag phenomena in our tension member, we are not going to use the effective area, or you can say that the effective area is equal to the net area. Okay, so this is, you just remember that what is shear lag we are going to discuss in the coming slides. Okay, so please remember that how we can calculate the net area. Okay, so you can go here and you can see that the gross area, you have to subtract the whole areas to get the net area from the gross area. Okay, and if the cross-sectional area is reduced somewhere, the tensile capacity of the member is also reduced. Is that clear to all of you?
यस
अभी
सर।
क्लियर हुआ आपको? नहीं हुआ तो बता देना।
क्लियर हो गया सर।
देखिए, shear lag phenomena, I will discuss it. Okay, just give me few slides. Shear lag phenomena occurs in those members when the member is not completely connected to the connection. So what happens that one part of the member is fully stressed and the other part of the member is not stressed to its full capacity. Okay, so there is a lack of stress transfer, and that lack of stress transfer we call shear lag. Okay, there are some examples of the real structures of tension member. Like for example, you can see this is a cable stayed bridge. Okay, this is a tensile member. Okay, this is a tension member. The bracing in the building are when they are subjected to some lateral loading, so they can develop tensile forces. So they can be designed or analyzed as tensile members. Similarly, over here, that hangers or the space trusses, they also contain the tensile member or the tension members. So it is very common to find tension members in your steel structures. Okay, or you will encounter tension members whenever you are designing your space truss or trusses or towers, transmission towers or bracing system. So some of the members you have to design as a tension member and some of the members you have to design as a compression member. Okay, okay. Now let's discuss about the failure modes in the tension member. Okay, please remember there are four failure modes in the tension member. I will write it down here. The first is the failure mode is the excessive deformation. The second is the fracture. The third is the sorry, block shear. And the fourth failure mode of a ten, which can be attributed to a tension member, will be the connection failure. Okay, connection failure. Okay, these are tension member can fail. Okay, these are failure modes of tension member. Okay, now the first is the excessive deformation. Okay, excessive deformation occurs in the region of a tension member which is not connected. Okay, in this region we will have yielding, and after the yielding we will have the excessive deformation. So a tension member can fail due to excessive deformation in this region. So this is the first failure mode in the tension member. Okay. The second mode, we know that it's the fracture, and this fracture occurs at the connected part of the tension member. Okay, fracture will occur in this region. Okay, and this fracture occurs due to the presence of the holes. Okay, and this presence of holes, what we have, what they do, they reduce the cross sectional area. They reduce the cross sectional area. Cross sectional area. And we have this area here we call net area. Okay, because and over here in excessive deformation we use the area gross area. Okay, so this is the first failure mode, and this is the second failure mode, and the third failure mode is the block shear failure. So the block shear, you can see that it occurs in the connection. Okay, what happens that whenever a tension member is subjected to loading, so it connection or a rectangular portion, you can say that this portion tears out. Okay, this may tear out, and once this type of failure we call block shear failure, and we are going to discuss what we call block shear failure. Okay, so the fourth mode is the failure of connection. Okay, if the connection fails, how strong is your uh, tension member? If the connections are weak, so what will happen that, for example, these are the bolts, and these bolts have very low shear capacity. So what will happen that these bolts can fail very quickly. Okay, so if they fail, it means the failure, it is the failure of the whole member. Okay, this is a local failure, but it is considered as the global failure. Okay, so these are the four modes, failure modes in tension member. Any question? आप
No,
लोगों को
sir.
समझ आ रही है?
Yes, sir.
खैर, जब आप लोग थक जाए तो मुझे कहीं रुक जाए तो मैं रुक जाऊंगा. ठीक है. Okay, now the next is the we have discussed the failure modes. ठीक है, कौन कौन से failure modes हम लोगों ने discuss किए?
Sir, excessive deformation, fracture, block shear, and connection failure.
Thank you very much. Okay, now the limit states. Now we will discuss the limit states. Okay, what are the two? There are here are in the tension member. Or what are these two limit states? Generally, we call them excessive deformation. Excessive deformation is the first limit state. If we have this limit state reached in the member, it means the failure of the member. The second limit state or design limit state we call fracture. Okay, these are the two limit states, and in this slide, so we are going to discuss the excessive deformation. Okay, so you already know that in this region, the connected part of the member, you have a reduced area. Okay, over here the cross-sectional area is reduced. Okay, cross-sectional area, the cross-sectional area in this part is reduced compared to this. So we get the net area in this region, and we get the gross area, and the net area is less than the gross area. So whenever the load is applied to the member, so what do you think, where will the deformation occur first? Here or in this region? There are two regions. What do you think, when the member is subjected to the axial force or tensile forces, in this region we have a reduced area, in this region we have a more higher area, a higher cross-sectional area. What do you think, where will be the yield stresses reach first, or where will we can find the yield stresses, in region 1 or region 2?
Sir, region 2, sir.
Yes, because it has a reduced cross-sectional area. Okay, what do you think? What is the length of this region? This length is more or this length is more? Okay, which length is more?
L2, sir.
L2 or L1?
L2,
L2,
sir.
sir.
Okay, what do you think? Where will be the more deformation? In L1 or L2? Strain is L by delta
L2, sir.
L. Yes, in L2. Okay. Okay, we know that the yield stresses will first be reached in this region, but the length of this member is very less. And the length of the unsupported connected member is very large. You can consider that L2 is larger than L1. So the deformation that will be produced in this member will be higher in L2 compared to L1. And how we can calculate the deformation? So you can say that if you multiply, okay, I got this equation wrong, so I will write it here, delta L by L. Okay, if you want to calculate the change in length, okay, so change in length can be computed using this formulation. If the length is more, you will have more deformation. So over here, the length is more compared to this region. So the deformation that will occur in this region will be more. So we can attribute that the excessive deformation, or we can conclude that excessive deformation occurs in the unsupported part of the member. Okay, unsupported region. Okay, what do you think, that we have to use a gross area or we have to use a net area for excessive deformation?
Gross area, sir.
Gross area. So whenever we are evaluating the excessive deformation limit state, so we are going to use the gross area. Okay, and what do you think, where will be the fracture formed? फ्रैक्चर कहाँ पे आएगा?
सर दूसरे L1 पे सर.
L1 पे आएगा. ओके, so you can read out these statements. I have explained this all statement with the help of these notations. Okay, if somebody is not clearer, so they can also read out this statement. Okay, I cannot read it out, okay, because it will take a lot of time. So now the second limit state is the fracture. Okay, now we know that the fracture will happen, or fracture will be caused at the supported length of the tension member, and this fracture is due to the fracture is due to the presence of holes. Okay, whenever you have holes, what happens? Okay, for example, this is a region, okay, in which you do not have holes. So what will happen, the average stresses in this region will be, or can be computed with the help of, or tensile stresses can be computed with the help of axial force divided by cross-sectional area. Okay, so this is an average and tensile stresses which you can compute with this formulation. But whenever you have a hole, so the stresses distribution is non-linear. It becomes non-linear, and the variation is from higher to the lower side where you have the holes. Okay, so the stresses that are produced where you have this hole are 3 times of the stresses what you are having in this case. Okay, so so presence of holes causes yielding, and this is due to the stress concentration. Okay, presence of hole causes yielding. Okay, you have yielding due to the phenomena called stress concentration. Okay, over here you will have stress concentration. Okay, there will be yielding of the material. Okay, but this stress concentration is neglected. Okay, it is neglected. Why it is neglected? Because we consider steel. Okay, because we consider steel as a ductile material, ductile material. So what happens when you have high ductility material or ductile material, that whenever you have stress concentration, this concentration is redistributed in the member due to the ductility of the member, and that's why we ignore this stress concentration. Okay, so we assume that due to the ductility of this material, the stress concentration will be redistributed in this region. So you can go through this statement. This all what I have said has been listed in this statement. Okay, so please remember that due to the presence of holes we have fracture, and due to the presence of holes we have stress concentration, and this stress concentration is neglected. Okay, okay, but but your material is not ductile, so your material is brittle, so you can have fracture. Okay, over here. So far what we have discussed, that there are two limit states. In one limit state we call excessive deformation. The second limit state we call fracture. And due to the presence of the holes, the area what we are going to use in the design or analysis of tension member, we call it net area. Okay, whenever we talk about fracture, the gross or the area which is used in the evaluation of the capacity of the tension member, so we are going to use net area. We are not going to use effective area. Okay, clear है आप लोगों को?
Yes, sir.
Okay, good. So now we move on to the, now we are sure that we have discussed two limit states. What are the two limit states in tension member? Design limit state. What are the two design limit states? One is the excessive deformation, and the second limit state is the fracture. Okay, I will write it down here so you guys should remember. In this we are going to use the gross area, and in this case we are going to use the net area. Okay, so in this graph or in this slide you will see that the comparison between the force and the elongation is made here. Okay, this is a pen. Okay, I have taken this slide from the lectures of a professor. Okay, so I could not eliminate this one. Okay, I'm sorry. So when you see that there are two lines, the first line is the blue line, and the red line is there is a red line. Okay, so the blue line is representing the yielding or the excessive deformation limit state, and the red line is representing the fracture. What do you think, which limit state is more preferable?
Fracture, sir.
Why
Sir, it's governing in this case, sir.
is preferable? Anybody else from the class? Like you are designing your steel, okay, and you have fracture, you can have this one and you can have this one. Which is more preferable? You want to go with this one or you want to go with this one?
Sir, ductile behavior.
Ductile, yes, you will go for the ductile failure. Okay, because you will get a warning and this will be very all of a sudden. Okay, so what you can do is you want to avoid this one and you want to prefer this one. For example, we have an approach we call AST. So what you are going to do is that for this fracture limit state, you are going to use a higher factor of safety. And for this case, you are going to use a less factor of safety. Okay, so you are allowing this limit state to occur in your region, in your member, and you do not want to have this limit state, so you can use higher factor of safety, okay, to limit this phenomena. Okay, so another important thing is the residual stresses. So residual stresses also causes early yielding. And this yielding, what are the residual stresses? The stresses that are induced in the hot roll members in the manufacturing process. Okay, due to the geometry of the member, for example, you have a wide flange section, okay, or W section. So this tip will cool fast, okay, because they are hot rolled, okay, hot rolled. So what will happen that compressive and tensile stresses will be produced in your member, okay, before application of the load. When the load is applied, the member in which you have the tensile forces, okay, so they will add to the stresses that are produced by the applied loading. So this we call residual stresses, okay, the stresses which are produced during the manufacturing, and these stresses are added to the applied stresses, and the yielding of the member is caused very earlier, okay, because if you consider that in the member we do not have any residual stresses and they are actually there, so they, when you load that member, so what happens that your stresses or your member reach the limit state earlier than you are expecting. Okay, now as I know, as we discussed that any tension member, for example tension member, they are subjected to the axial forces, but they need to be connected, okay, as well. Okay, and we have discussed that when we are talking about the connections, the connections can be riveted connections, the connections can be welded connection, they can be bolted connection. Okay, so this graph is showing the performance of a tension member with with bolted and welded connection. The green line is representing the behavior of tension member connection, or tension member you can say, which is bolted with high strength bolts. Okay, and the second, the blue line is representing the tension member with welded and riveted connection. So which performance is like desirable, this one or this one?
Bolted, sir, in this case.
In bolted connections, if you see this initial part, there is a plot between the force and the elongation, and you can see that during the up to here, the performance of welded or riveted connection and the bolted connection is almost the same. But what happens that you have slippage, okay, in the bolted connection, and in the welded or the riveted connections, you do not have the slippage. Okay, once you have slippage, what is the type of bolted connection it becomes here in this region? This
Bearing type,
is
sir.
bearing type. It becomes bearing type. Initially it was a slip critical connection. Okay, oh, in this region the bolted connection was a slip critical connection. Okay, so you once what is the failure of a slip critical connection? Once you whenever you have slippage in your connection, the connection is assumed failed. Okay, so what you do that whenever you have a very dynamic loading or impact loading or fatigue loading, so you always go for this connection. You do not want to have any slippage in your member. Okay, okay, now as I told you that cross-sectional area, we started with this one, that the cross-sectional area of the tensile member of tension member is the only or is the determinant of the strength of this tension member. Okay. So now we have two approaches. One approach is LRFT and the second approach is AST. So now we can see that how we can uh, evaluate the capacity of a tension member for two limit state. The first limit state is excessive deformation. The second limit state is fracture. So in evaluating the capacity of tension member against excessive deformation, we will use grass area. In evaluating the fracture capacity of the tension member in fracture, we are going to use net area. Okay, not effective area. We can use effective area if the shear lag is there. In shear lag phenomena is there, then you have to use the effective area. Okay, now in yielding case or the excessive deformation case, you use yield stresses at yield, and in the fracture criteria or limit state, you use ultimate stresses. Okay, so what do you think, what is the Fy value for A36 steel and what is the Fu value for A36 steel?
Sir, FY is 36 KSI and FU is 58 KSI.
58 KSI. Okay. Now, this is the, what you have not asked me that why you have written excessive deformation. Okay. Now, why it is written yielding? Because if we want to prevent the excessive deformation, we have to prevent the yielding to occur in our member. Why we have excessive deformation? Once the stresses are beyond, when they have crossed the yielding stresses and they go into the non-linear range, and then you have very all of a sudden high deformation in your member. So that's why instead of, in order to take care of excessive deformation, excessive deformation, we limit the stresses in our member not to reach yield. Okay, this is excessive deformation and this is for fracture. Okay, since we are talking about the LRFD approach, the strength reduction factors which are going to use is, we are going to use 5 for excessive deformation, 0.9, and for fracture we are going to use 0.75. So we are reducing the fracture strength because this is more of a serious nature. Okay, this is brittle failure and this is ductile failure. So this is reduced more. Okay, so now the basics philosophy of LRFD design is that your demand should be at least equal or less than the capacity of your member. And what are those capacities? These two are the capacities. So you have to select the least out of these two capacities. Okay, so this is what we are saying, what I have explained, that okay, the demand should be less than or equal to the capacities. Okay, so these capacities you have to take the least, you have to compute the capacities. Okay, and then you have to take the least out of the two. Okay, in this way you will proceed. In LRFD, sorry, in EST, allowable stress design or allowable strength design, So you have to have the required strength. This is the required strength. Should be less than or equal to the allowable strength. Okay, this is allowable strength and this is the required strength. Okay, this is required and this is allowable. Okay, so in ASD we have to evaluate for the excessive deformation, or we call it yielding. So we have to use different factor of safeties. Okay, this is gross area, this is FY, and this is effective area, this is FU. The factor of safety here is less as compared to the factor of safety we are going to use in evaluating the fracture capacity of your tension member. If you simplify this, so you can also you will get this formulation. If you go 1 divided by 16.7, or you do 1 by 2 here, so this will change. Okay, in rather than using this notation, you can use this notation as well. So there are different materials. Okay, the FU and FY we have to use in the evaluation. Like, what are the stresses we are going to use? FU and FY. These FU and FY you can find in the AISC manual. Okay, but most frequently, we use A36, and this is 36. Okay, and this ranges from 58 to 80. Okay, so these are the preferred shapes, which type of shapes are preferred for which type of material. Okay, so mostly A36 steel is for wide flange miscellaneous S. Okay, now this information you can find in the AISC manual. So I will encourage you to open up that manual and go and look for these tables. Look for these tables. Okay, in order to know the different steel materials and their properties. Okay, now let's go through example. Okay, now you have to, there is a plate which is connected to a gusset plate. This is a gusset plate. Okay, this is a tension member, and it is a plate which is ½ inch thick. Okay, and it is connected to this gusset plate with the help of these bolts. Okay, now if you see the section, so you will see this one. Okay, now what you have to do is, the steel which you are going to use here is A36 steel. Okay, this is A36 steel. So what we have to do, we have to find these capacities. And what are those capacities? We have to find the design capacities. Okay, one is the 0.90 AGFY. This is LRFD. A net FU. FY and FU you already know. For A36, FY is 36 KSI and FU is 58 KSI. Grass area you can calculate. Net area you can calculate. Okay, how we can calculate the grass area? We can multiply this here. We have these two dimensions, grass area 5 into half. So you will get this grass area. So you can calculate the nominal excessive deformation capacity. For fracture, you need to know the net area. And how we can calculate the net area? We have to subtract the whole area from the gross area. This is grass area. And you have to subtract, this is the thickness of the plate. Okay, this is the whole area. Okay, what is the whole dimension? How we can, just give me a moment. मैं बैटरी मेरी ड्रेन हो गई थी, सॉरी, मैं चार्जर कनेक्ट करना भूल गया, तो इस वजह से ये मैं डिस्कनेक्ट हो गया था। आप लोग मुझे सुन सकते हैं?
यस सर, सुन सकते हैं।
चलें ठीक है, मैं अभी जाता हूँ और मुझे फिर वो करना पड़ेगा। ओके, लेक्चर नंबर 5, वेयर इज लेक्चर नंबर 5? नौ बज गए, हाँ। ओके, कहाँ था मैं? ओके, वेयर वर वी? We discussed this one, we discussed this one, we discussed this one, this one, this one. Yes, we were here somewhere. Now, एक चीज आप लोग नोट करें, this is a very simple exercise, okay? This is a very simple problem, but please remember that how this net area is computed, okay? Please pay attention to this one, okay? There is a trick. What is the trick? Why two holes are being used? Firstly, if you go back, the diameter of the hole is, let me write it down here, okay? I'm sorry, the diameter, okay? This is the diameter of the bolt. The diameter of the bolt is 5 by 8 inches. What should be the diameter of the hole? 1 by 8 clearance. So this should be 6 by 8, okay? So we will see that in computing the net area, so it is multiplied with 2 holes. Why 2 holes? Why not 1 hole? If you see that this is the load application, okay? Okay, the fracture will occur in this pattern. So the fracture part will be crossed by 2 holes, okay? That's why you have these 2 holes, okay, which are subtracted from the grass area, okay? So in this way, you can calculate the net area. So in this case, the net and the effective area, we do not have shear lag. We are neglecting shear lag. We are neglecting shear lag. So the AE is equal to AN. Okay. So you can calculate the effective area. Then you can calculate the fracture strength capacity of the member. Then you can go for the capacity. So out of these two capacity, this is the lower one, so this is controlling, okay? And if you move on to the allowable stress design, so allowable stress design, we have to know the capacity, okay? What is 90? Let me see. 90 is what is this one? Let me go through it. Where is that 90? This 90 is not mentioned in this example. What is 90, sir? किसी को अंदाजा है? Okay. This is, we have to use this one. Yes, yes, no, sorry, I got it wrong. This is PU. This is PU, okay? This is not PN. So this is 90 nominal capacity, okay? What you are going to do this, you have to divide this nominal capacity by 2 factor of safeties in order to get the yielding strength or the excessive deformation strength, and for fracture strength you have to divide by 2. So this is least of these two, so this is controlling. The fracture is controlling. Controlling means this capacity will reach first, then this one. Okay, so you have to use the least capacity. So least capacity will always be controlling. So if you do not want to use this notation, so you can evaluate the AST capacity using this formulation. If you remember that in AST we had this capacity, this formulation. Yeah, where is that? No. मैं आगे चला गया. This one. So you can use 0.6 Fy and Ag in order to evaluate the excessive deformation capacity, and you can use 0.5 Fu Ae to evaluate the fracture capacity. If you are not you do not want to use this notation of ASD, so you can use this notation. Both will yield in similar results. Okay. Clear है जी? आप लोगों को क्लियर है कि नहीं?
Yes, sir.
थक गए हैं लगता है. Okay, we will go through another example. It's a very simple example, and please pay attention. What is happening? ये कहाँ पे जा रहा है? We have a single tension member which consists of this angle, okay, which is connected to a gusset plate. Diameter is 7/8, A36 steel. The service loads are P dead is 35 kip and P live is 15 kip. Okay, now you can see that this member is connected to this gusset plate. This is a gusset plate, okay, and the load is applied in this direction. And once you calculate the net area will cause fracture in this dimension. Once you calculate the net area, so you have to subtract single hole area out of gross area, okay, one whole area. Okay. So one thing is that in this type of member, when one part of the member is connected and the second part of the member is not connected to the gusset plate, so this member is not completely connected with gusset plate. So in this type of member, we have this phenomena, shear lag. This phenomena we call shear lag, which can occur in this type of member. Okay. So in this case, you will have some effective, you will use effective area. You will not use this one. So effective area and this area are interrelated. And this U factor is given here. U is 0.85. Okay. लेग का आइडिया हुआ आपको? शेयर लैग का कुछ आइडिया हुआ आपको? शेयर लैग फिनोमेना का किस किस्म के मेंबर्स में शेयर लैग होता है?
Yes, sir.
Okay, I know you are tired. Okay, if we go through the capacity, so if you want to evaluate the tensile capacity, basically you have to do it the same way that we did in the last example. So we computed this excessive deformation. دا مخامخ داس چلو کې دا بر اخ scientific instrumentation کې دی او ولته لاړ شي. Sorry, excessive deformation, and we have to evaluate the fracture. Okay, how we can do excessive deformation capacity, phi AG FY, and how we do that, phi AE FU. Fy and Fu are known. So we have the gross area, and if you want to find the gross area of this angle, okay, this angle, which is that angle, L 3 by 2 cross 3 by 2 cross 3 by 8. So you can go to the AISC manual and you can look for this shape and you can get this area. Okay, so you know how to this is the nominal capacity. Okay, so this is 90 kips. So the net capacity, now you can see that there is one whole area subtracted from the grass area, and I told you why it is one whole this time. Okay, and how effective area is calculated. Okay, now this is the least capacity. Okay, so whenever we talk about this, we have to compare this capacity with the ultimate load demand. What is the demand? We have two type of combinations. PU is 1.2 P dead plus 1.6 P live. Okay, so you have to use the maximum out of these two. Okay, based on the nature of the loads which are present on your structure, in your structure. Okay, so the PU value, what is the PU value? Okay, we will see the PU value you can see is 66 kips. This is more than the first combination. Okay, this 66 kips is less than this capacity, so we are fine. Okay, now whenever you want to do the AST, so you have to divide the nominal capacity by the factor of safety, and then you have to compare it with the demand, and the demand will be calculated. The factors will not be used in once we want to calculate the demand for ASD. You just have to add 35 plus 15, it is 50. So the least value out of these capacity is 52, and this 52.4 is more than 50 kips. So we are fine. If you want to use this formulation in ASD, go ahead, you can use it. It is open. Either you can use this formulation or either you can use this formulation. Okay, these are the same things. Okay, so there is a home assignment. Okay, so you can go through the example number 3.3 from the SIGWI book. Okay, now now we will discuss the joint efficiency. Okay, the joint efficiency, we know that every member, every other member, like every other member, the tensile member is also to be connected. Okay, they can be connected via bolts, rivets, welds. Okay, so the joint, if the joint fails, if this fails, it means failure of the tension member. If this fails, means the member fails. Okay, so there are some aspects or properties which control the joint efficiency. The joint efficiency is very important. There are different things which control the joint efficiency. We have to take care of all these aspects when we are designing the tension member. Okay, tension member. Okay, tension member. Please remember, tension member design or analysis not only means design of the member, but also design of connections. Connections plus member itself. Okay. So the material ductility, we know that if the material is ductile, there will be no stress concentration. The fastener spacing we have discussed in the connection, okay? So we have seen that there is a stress concentration in that holes. The fabrication process, what are the different fabrication process which are being used for the fasteners. Then this is shear lag. So 5 things, 1, 2, 3, 4, 5. The first is ductility. The second is the fastener spacing. The third is the stress concentration. Fourth is the tightening procedures of fabrication. And finally, the shear lag, okay? So once you have shear lag, so as I discussed that whenever we are evaluating the fracture limit state, fracture limit state, so we have to use effective area, not net area. And how effective area and net area are interrelated? They are interrelated with a factor called U. Okay, once if you have a bolted connection, so this effective area is related with the net area. And for the welded connection, this effective area is related with the gross area, because the cross-sectional area, or that there will be no net area in the case of welded connection, okay? So for welded connection, gross area. And this relationship holds between the for bolted connection as effective area and net area. If all elements of the connections are connected, then there will be no shear lag, okay? If any part of the member is not connected, so then you will have this shear lag, okay? Okay, now this, there are U values. These are the simplified values. Simple guidelines. How to use different U values. Okay, for example, if you have 3 fasteners, at least 3 fasteners per line in the direction of applied load for the case of wide flange, miscellaneous or S shape with width to depth ratio at least 2/3, okay? So you should use U 0.9, 3 fasteners. If for other than these shapes, these for all shapes, you should use U is equal to 0.85, 3 fasteners, okay? If only 2 fasteners are there, then you have to use U is equal to 0.75. Now let's come to the shear lag, okay? Now shear lag, for example, there is a, you can see there is an angle which is connected to this plate, okay? And there is an applied load. So when the load is applied, okay, this member is welded. This is welded. And it is welded. So what will happen that when the load is applied, this member is fully stressed. And this member will be, fully stressed. And this part of the member will not fully stressed, okay? So there will be a lag of stress transfer. So you can see that stress transfer in this member, and you can see the stress distribution in this member. So there will be stresses will be lagging in this member. And once you have this type of scenario, we call this scenario or this situation shear lag, okay? So this is more descriptive on this slide. So there is an angle, and this angle is connected to this plate with some fasteners, okay, some bolts. What will be the distribution of stresses? So this member will be fully stressed, and this member will be not fully stressed, okay? So once one element is connected and one is not connected, so you should expect this shear lag. And for shear lag, you will use effective area, which is a function of net area, and this is a function of gross area for welded connection, and for bolted connection you have this relationship. Okay, now the thing is that how we can find the U values. So U values, we have seen the simple guidelines in the previous slide, but in order to compute the U value, you can use simple equation. Based on the configuration of your connection, you can use this relation or equation to calculate the U value. So what is 1? 1 is a constant. L is this one. For example, again there is a pen. I apologize for this image. Okay. So if the load is applied in this direction and only this part is connected, okay, the part which is connected, that will be L. Okay. What is X bar? X bar is the distance of the centroid of the member up to where it is connected. For example, you can see that these are two channels. This is a two-channel section. And you can see that the centroid is from this to the point where it is connected. In this case, you can see this is a simple example of a single angle, equal leg angle. So the centroid of this angle is here, and this angle is connected up to here, this point. So this X bar will be from this to the centroid. Similarly, for the wide flange section, if the plates are connected here, so then you have to use this X bar. If the plates are connected here, you have to use this X bar. So the point is, okay, this is a simple equation. How we can obtain this X bar? This X bar you can obtain from the shape. AISC manual. Okay. Please remember what is L and what is this. Okay, so there are more guidelines. Okay, if there is a single angle and it has 3 fasteners, so you can use this U value. If there is a single angles and you have 4 bolts, 0.8. Similarly, if you have this type of situation, and if you satisfy these criteria, you can use these direct values. But if you do not want to do that, you can use this simple equation. Now there is an example, like there is an angle. Okay, so this which is being connected. Okay, this is an equal leg angle, and if you want to find about X bar, you can go to the manual, and you should try to find this section, and you will get this X bar. This X bar is given here, but maybe for some problems it is not given. You have to find the bolts are 5/8. The center to center spacing is 6. So this will be L. Okay, this will be the L in this equation. This is L. X bar is here. You can simply use these values and you can calculate U, and then you can you can calculate the effective area from the net area, because this is a bolted connection. When bolted connection, you have this relationships hold. First, you have to calculate the gross area. You can obtain that from this manual, and I encourage you to use this manual. Look for this shape, 6 cross 6 cross 1/2. What is the gross area? So you will get it in inches square. Okay, so the whole area, how many holes we have? Let me see. Let me go back. If the load is applied in this direction, what will be the fracture dimension? Will it be in this direction or will it be in this direction? क्लास। फ्रैक्चर की डायमेंशन किस डायरेक्शन में होगी?
हॉरिजॉन्टल।
ये अगर लोड है तो इसके परपेंडिकुलर होगी। अच्छा, इसलिए मैंने बताया इस तरह होगी। अच्छा, ये पिछली बार मैं बता भी चुका हूं, लेकिन आपको इसलिए बता रहा हूं कि आपको याद रहे। ये कितने होल सब्ट्रैक्ट करेंगे ग्रास एरिया से?
2 सर।
कितने?
टू
वन,
सर।
टू?
सर 2
टू
2
होल्स, यस। तो टू होल्स, this is the thickness. So you can calculate this one. Now what you have to do, you have computed the net area, so you can calculate u. 6 is, this L is 6 by 6 by half. This 6 is not this one. This is, sorry, this L, this L. So you can calculate u comes out to be 0.72. So you have net area, you can simply calculate the effective area. Once you have calculated the effective area, okay, so you can go through this statement. Okay, this statement you have to go through. Either it's this statement is saying that you can use the simple recommendation or it, but they are not that accurate, and in order to get the more accurate value of u, you have to use this equation. Okay, so similarly you can calculate E, or then what you have to do, you can evaluate this capacity. For example, ASD, कि आप लोगों को याद रहे, आप A ग्रास यूज करेंगे, और फॉर फ्रैक्चर यू आर गोइंग टू यूज AEFE. AE आपने कैलकुलेट कर लिया इस एग्जांपल में. ओके, so I would suggest that you always use this, and you should start using your manual. Okay. Okay, just last question, one question. Shear lag, this is angle, this is a welded connection. Which equation will hold to compute the E, effective area? This one or this one? कौन सी इक्वेशन हम यूज करेंगे?
AG वाली सर।
सेकंड वन सर।
Yes, correct. What will be the L value?
The
Give
length
me
of
the L
weld.
value. Huh? What is
Sir,
L value?
horizontal length of weld.
कितनी? This one. For example, if you had unequal weld, यहाँ पे वेल्ड ज्यादा हो और यहाँ पे वेल्ड कम हो, तो फिर हम ये वाली यूज करेंगे. ठीक है, अगर बराबर हो तो फिर एक कोई एक भी आप यूज कर सकते हैं. ठीक है, इज इट क्लियर? फॉर एग्जाम्पल, अल्लाह के बंदो, मुझे थका दिया आप लोगों ने. ये वेल्ड है, ठीक है, और यहां से भी वेल्ड है, और यहां पे वेल्ड लेंथ ज्यादा है इससे. Then you have to use this one. This will be your L. This will not be your L. Okay. Is it clear? Is this thing clear?
यस सर।
चलें इस तरह करें, ब्रेक ले लें, मैं भी थक गया. So this is 9:30 now, and we will meet back at 9:45. Is that okay? ठीक है, 9:45 कि नहीं? क्या कहें, मुझे तो पता भी नहीं
यस
है.
सर। यस सर 9:45 ओके।
ठीक है, चलें.